So in the class today, we're going to talk about a new type of database, specifically graph databases. And we're going to focus mainly on one type of graph database, which is Neo4j. After I motivate maybe a little bit more the need for, or the use cases for graph databases. So we've spoken about NoSQL, and we've spoken about key value stores, column families, document databases, and finally, we're going to talk about graph databases as the fourth main category of NoSQL store. So there's been a lot of increasing attention on using graphs to manage data recently. There's been a lot of talk about the notion of knowledge graphs, which is this idea of modeling diverse data using graphs, where nodes in the graph represent entities and edges represent relations between those entities. So this started in, I believe it was 2013, Google announced their knowledge graph, but now many companies are using knowledge graphs for modeling diverse data, useful for their applications. Also, there's Facebook Open Graph protocol, which is used, for example, for modeling sort of likes and information about pages on the web. There's this GraphQL query language, which actually is not so related to graphs. It's a bit different, but it allows better organization of APIs on the web, and it's also become quite popular. It was proposed by Facebook. And for example, Amazon have, in the past few years, maybe 3-4 years, they've been developing a graph database specifically that you can run on Amazon Cloud, on Amazon Web Services, for example. So this is just a taste to give an idea that graphs are becoming more and more popular in terms of modeling diverse data. They're becoming more and more popular in practice. So we see some growth in our Google Trends for graph databases, suggesting perhaps an increase in the interest in using such databases. However, it's important to put it into context that it's still a fraction of the attention or the use still for relational databases. So it's increasing, but they don't quite approach the popularity or adoption of relational databases still. Okay, but focusing on the growing attention, I think it's interesting to know about graph databases. So what is a graph database? Effectively, we have two main models in practice, and we have some variations of those models, but we can think of two main models that are common in practice. The first is called the directed edge label graph, where we just have nodes that represent entities like specific stars, specific planets, types of planets, and so forth. Nodes can also represent data types like numeric values or strings. And we just connect those nodes using edges with labels. Okay, so if you've taken the course La Web de Datos before, this might look familiar. This is very similar to RDF. We can query this using Sparkle. But for now, the main focus is just to note that we have nodes, we have edges, and the edges have labels. So, and the edges are directed. So we have a directed edge labeled graph. So we can model arbitrary data using this model, and it's quite simple. A second model that's become popular in practice for graph databases is the property graph model, where we add some additional details to the nodes. So we don't just have simple nodes, but nodes can themselves have these sort of property value pairs, where we can define more information about those nodes. Nodes have labels to indicate the type of node. They have an ID. In this case, I write N1, but this would be maybe a 64-bit ID, for example. The edges can also have labels and can also have some metadata, some properties and values attached. So, however, we see that the general idea is more or less the same. We have nodes and we have edges that connect nodes, and those edges have some label, have some information associated with them. So we can attach additional information here to nodes and to edges. but the overall structure remains more or less the same. And we can query this then in languages such as Cypher that we'll speak about later. So we have dedicated query languages for graph databases. I'm not sure if I mentioned here, sorry, this query is in the syntax of Sparkle, which is a query language for RDF. We're not going to focus so much on that in this class. We're rather going to focus on property graphs and the Cypher query language. RDF and Sparkle is something I talk a lot about in the other course, along with the Datos. Okay, so taking a step back, why? Why do we need graph databases? Why is it interesting to, I mean, why not just use a relational database, for example? So the first answer is flexibility. So I present the similar slides in some other classes, maybe you've seen them before, but when we speak about relational databases, we have all the sort of very well organized rectangular tables where we can insert our data, and we should try to avoid nulls, and we have to define exactly what kinds of data we're going to store and organize them very well. And so everything is very organized and well structured and easy to find. However, in certain cases, it can be, in some cases, it can be easy to structure our data like this. Like, for example, in the case of a bank, we should be able to anticipate what sorts of data we're going to need to store, and changes to the schema in terms of what tables we store, what columns they have, what are the keys, should be relatively static. We're not going to change them too often. But if we take other scenarios where we're not sure beforehand what we want to store, then it can be difficult to use a relational database. So in this particular example, I'm going to assume that we are going to describe and index some data about planets. And at the start, we don't know what we want. We just want to collect as much data as possible about planets. So we might start with the names of the planets, where we have the name as the primary key, meaning that we can't have two names in this table the same. We can add some information about distances and keep adding some more, filling out our data, leaving nulls in these spaces here. Information about the radius of the planet, the gravity. We can continue adding more data, the length of the days, years, the temperature, whether or not it has a ring. So this table is looking pretty nice. So if we assume now that we want to model information about the satellites, the moons, the natural satellites or moons of the planet, we could think about adding another column here, but some planets might have no moons, some planets might have multiple moons. So what we would rather have to do, if we remember our database course, is think about defining moon as a separate relation. Okay, so defining a moon table here, and then giving the names of the moons and the planets. In this way, we can represent a 0 to many relation. So maybe we want to extend some information about the moon, and we want to add some information about who discovered the moon. In some cases, maybe we need to provide nulls, either because there's no clear value, or because it's unknown at the moment. So this is the year that it was discovered. So, okay, we have some nulls here. This is not great, but maybe, we can tolerate the nulls for now. If not, we can maybe, generate a new table where we have the name of the moon and who discovered it, and this allows us to avoid nulls if necessary. We can also do the year of discovery as a separate table if necessary. So, okay, what happens here? We have a reference to this table. So we would assume that all of the planet names that appear here should also appear here. Okay, so we can define maybe a primary key or a foreign key. So we can say that this column here is actually a reference to the primary key name of the planet table. So anything that appears here must appear as the primary key here of planet. So, okay, we have our schema, we have things looking more or less stable. Now Pluto is no longer a planet. We have to somehow do something with Pluto. How are we going to resolve this issue? Well, rather than just delete the data, maybe we'd like to hang on to this data in case it might be useful in future. We could say, okay, let's create a separate table, dwarf planet, and we'll add Pluto to the dwarf planet table. So great. However, there's a problem. Great. Anyone, maybe can someone see the problem with doing this?
Yeah, we still have Pluto in the moon table.
Yep. So this foreign key here says that Pluto must appear here, and it no longer appears here. So it's now in a different table. So now, actually, yeah, we have a problem. So we have to resolve this. So how do we resolve it? Well, the hint is that there's no nice solution here. We could maybe try to define a sort of more generic planetoid table or something like that. Or maybe we have a dwarf moon table where we have the moons of dwarf planets. Or maybe we drop the foreign key, or or maybe we somehow use a view or something. It becomes very messy, right? So probably the simplest would be just to drop the foreign key for moon. So let's drop the foreign key for moon. Okay, so now we want to model also planets that are exoplanets that are orbiting other stars. Okay. So if we think about that, okay, at this stage, we're going to get pretty tired because every time we make a change, we have to change the definitions of the keys, create new tables, extract columns, add them to other tables. It's just at every step, we're updating the schema as well as the data. And it's sort of inflexible and kind of slow. This is because we don't know a priori what data we want to store. We don't want to, or it's not feasible maybe to to define a schema up front, a relational schema in terms of these are my tables, these are the columns of those tables, these are the primary keys, these are the foreign keys. It's difficult because we don't know at the start what we're going to store. If we compare this with something like a graph database, we're going to do something similar about modeling planets, but this time in a graph model. So we can start with a node like Earth. Okay, we know Earth. We can create a star, sun. We know the sun. We can connect them. We can give a name to that connection, parent, for example. We can add also in this direction, sun, child, Earth. We can add another node, Pluto, and add some connections. We can continue adding nodes and adding edges between those nodes, and so on and so forth in a relatively flexible way. So, yeah. Is there a question? Oh, we're good. Okay. So if we come to this point and now we say that, okay, Pluto is no longer a planet, what do we need to do? It's nothing dramatic, right? We drop this edge. Pluto is no longer an instance of planet. No worries. And then we just add a new node, dwarf planet, and we connect Pluto directly to dwarf planet. And we're good, right? So if we want to model exoplanets, that's fine as well. We can, well, I would imagine all the exoplanets we know are in the Milky Way. But anyways, we can add information about galaxies and so forth. So it shouldn't be an issue. So we can continue adding more information, enriching the data that we have as we wish in a much more flexible way than what we would do for relational databases. So we can add information about galaxies, other solar systems, whatever we would like to add, and so forth. So we see that with respect to relational databases, graphs have some pros, some advantages, and some cons, some disadvantages. So in terms of the cons, the disadvantages of a relational database is we have to impose a schema, a structure on the data from the start. And as the data change, we might have to update that schema. The good news is that we have a structure or a schema imposed from the start, and that can be a very good description of what the data we have are. We can tell someone, here's my tables, here's the columns I have. And that gives a very good summary of what's in the relational database. It also makes sure that all of the data thus far follows this structure. So the data are more regular. So somehow it's this idea that you specify some rules and regulations for your data at the start that the data must thereafter follow. And it's kind of a more rigid structure. In terms of graphs, the benefit is that we don't have to impose a structure or a schema from the start, which is great if we don't really know what we want to model yet. And the disadvantage is that we don't have a structure imposed from the start. So the data can be a bit more diverse. People can introduce different edge labels to mean the same thing. The graph itself can be difficult to describe and so forth. So it's a little bit less structured, but that flexibility can be useful in many applications. So it's somehow, I don't want to say that graphs don't have structure. If people follow the kind of patterns they see in the existing graph and use the same edge labels and try to, not create duplicate nodes, then there's a more emergent structure that will occur over time. So it's sort of a more organic structure, but you can see that there's a structure there, assuming people, try not to define duplicate nodes or duplicate edge labels, try to follow the existing patterns, and then a structure will emerge. It's just not defined from the start. Any questions or doubts on that? So the key message there is that graph databases are more flexible because you don't have to define a detailed schema right at the start, right? Or you don't have to update it every time your data changes. You can sort of postpone, or even, it's optional to define a schema. You don't have to if you don't want to. Second good argument for graph databases is that they're useful for path queries. So in this directed edge label graph, for example, if we want to define all instances of astronomical body, we see that, okay, we have instance, we have nothing that's an instance of astronomical body directly, but we have TRAPPIST-1b, for example, that's an instance of an extrasolar planet, which is a subclass of planet, which is a subclass of astronomical body. So really what we'd like to ask is for instances of things that are transitively connected via subclass to astronomical body, right? So another example would be TRAPPIST-1, which is an instance of ultra-cool dwarf and red dwarf, which is a subclass of dwarf star, subclass of star, which is also a subclass of astronomical body. So in this query here, which I won't get into in too much detail, but what this says is get me all of the nodes that have an instance followed by 0 or more, a path of length 0 or more of subclass connected to astronomical body. And thereafter it looks for their constellation. But this allows us to effectively traverse in the query multiple subclass edges, or to traverse paths of arbitrary length. So this is pretty cool. And this is something that's quite difficult to do in relational databases. There are recursive features that would allow this, but it's not as intuitive as when you think in terms of a graph. So we can query arbitrary length paths. So in this case, what are we counting? We're counting what the query exactly is doing here. Again, not to worry too much about the syntax. It's counting how many astronomical bodies there are in each constellation. So in terms of Aquarius, we get that, we get the constellation of the body, then we group by the constellation, and we do a distinct count here, and then we order by count. So if we look at how many astronomic bodies are in Aquarius, it's the only constellation we mentioned. TRAPPIST-1b is an astronomic body, TRAPPIST-1c is an astronomic body, and TRAPPIST-1 is an astronomic body. So we can get all the astronomic bodies, no matter how long these paths of subclasses might be. To astronomic body, we can get that using a path query. So we see Aquarius 3. We can also do path queries as well in property graphs. We still have, edges, and if we follow a sequence of edges, that forms an arbitrary linked path. So in this case, this syntax, which I'm going to explain in more detail later, but just for now, what we're looking for are nodes which will match with the variable x1 that are labeled person. So that would be this node, this node, this node, and this node, but not this one because it's labeled post rather than person. So we match all nodes labeled person, and then we say also the first name should be Julie. So actually we rule out this one and this one, and we're just left with this node here. And then we say follow a path of nodes. It can be a transitive path of nodes to another node labeled person. So that would go to here, it would go to here and back here, it would go to here and to here, okay? But it could not go, for example, from here to here to here because this edge is not labeled with nodes, it's labeled with likes. So we should be able to reach Julie, John, and Frank from Julie, okay? And then we're looking for another condition, which is that the node that is connected, the second person, has to like something that has a tag, that has a follower, x1, okay? So it has to like, so let's say John, for example. John is the second person here. So John has to like something that has a tag, that has a follower, that is x1, and x1 was Julie at the start, right? So we see that John is a possibility. Frank, does Frank like something that has tag, that has follower Julie? Yes, so Frank would also be matching N2. What about Julie? So Julie knows John, who knows Julie, so x2 can also be Julie. Does Julie like something that has a tag, that has a follower Julie? Yes, so we would actually get the first names of these second people, which would be Julie, John, and Frank. So the key point here is that this star, this asterisk, allows us to navigate nodes once, to navigate it twice, to navigate it the number of times we want. So the results here would be Julie, John, and Frank. And we'll get into more detail in this query language later. Any doubts or questions? What I want to get across for the moment is just the notion of paths, kind of introducing query syntax and all this, but I just want to get across the idea that graph databases are cool because we can do these path queries. So could we end up with some kind of infinite loop using star? It's a very good question, and we could. So we have to be, when we define these query languages, we need to define certain restrictions on these paths. So common ones would be, we can't visit the same node twice. So somehow we have to stop at some point because we have finite nodes in the graph, or we cannot use the same edge twice. So once we use an edge, we can't use it again for our path, which stops these loops. These are called simple path semantics. Another type of semantics is shortest path semantics, where we only return the shortest nodes, the shortest paths between nodes. Another way is to only return pairs of nodes that are connected by paths rather than returning the paths themselves. So there are various ways, but there are indeed in the unrestricted case, infinite paths of nodes. So we could just keep on going around and around here, right? So that would create an infinite path. So we need some restrictions, and we'll talk about the restrictions that Neo4j applies later. Yeah. Okay. So what about property paths? Why do we need property paths? Directed edge label graphs look nice and simple. Why do we need the kind of extra details of property graphs? Well, we don't really, but they are popular as they're convenient in practice. So here we're representing some data, which is about who discovered which moons of which planets, okay? So we have the discoverers of the moons, of which planet the moon is orbiting and so forth. So, okay, we take this graph and then we ask, how could we say that Galileo Galilei discovered Callisto and Io in 1610? So how could we add the years to the discovery here? Right, so where could we add them? So not so straightforward, right? What we would have to do is create a new node, which is like it represents somehow the discovery of each room. So there's a new node that represents the discovery of EO, and there we can link that. Okay, the body discovered was EO, the year was 1610, the person was Galileo Galilei. So now we have, these graphs are very good for binary relations that connect two things with a given relation, but it's more difficult to represent n-ary relations where we have three things that are related. So Galileo Galilei discovered EO in 1610, a ternary relation. So to represent instances of these relations, we need to create nodes to represent them. So it's just sort of like thinking now that the discovery is an entity, right? The relation it becomes an entity, becomes a node. So we can decompose hierarchy relations with 3 things, 4 things, 5 things back down into binary relations again. It's a little bit messy, right? So we might say, wouldn't it have been nice to simply just be able to put the year on the edge? And it would, it would have been nice, yeah, because we have to do something here that's a bit, if we look at the difference between these two things here, we see that we have to implement quite a few differences or quite a few changes to our graph to be able to model this additional data. So it's not, it's not as simple as we saw before, just adding nodes and adding edges, right? We add new information here, and now the discovery changes from being an edge to being a node that's connected to all the elements of the relation. So it's a little bit, we might have to change the structure of some things. So it would have been nice simply to add the year, right? And this is sort of the idea in which property graphs are going. So property graphs, they already add kind of lots of slots for you to describe the existing nodes and the existing edges. And it's rare that you will have to, turn an edge into a node. So we see that we have lots of kind of places to describe nodes, to describe edges, to put dates on edges, for example, or to put more metadata, whatever metadata we like on a relation. So it just gives a little bit more space such that, we won't have to change the structure of the graph so often. And at the cost of having a more complicated model, right? So we have more details now to think about. So what do we have in the property graph model? We have attributes, property values on nodes and edges, these yellow things here. And we have IDs on nodes and edges. Here, these would, I'm not going to write out a 64-bit ID. Here, I'm just going to write E7 as the identifier for edge 7. But these would have some sort of internal bit string as an ID. And we have labels on nodes and edges. So here we see the labels. In the number of labels, the number of values we can have per property, these are details of a specific implementation of property graphs. So in the case of Neo4j, for example, it happens to allow multiple labels on nodes, but only one label per edge. It also only allows one value per property, but the value can be an array, right? So these sorts of details are maybe not so core to the idea of property graphs, but each implementation will define, slightly different variants or flavors of property graph. Okay, any questions or doubts? Okay, so this is the sort of abstraction of property graphs. So where are these things implemented? What systems, what graph database systems can we find? Well, if we look at our favorite database ranking that we've referred to many times, we see again the usual suspects at the start, where we have Oracle, MySQL, Microsoft SQL Server, Postgres, and so forth. And MongoDB being the most popular NoSQL store. And if we scan down along looking for graph, we find graph in position 18. Okay, so the most popular Neo4j, the most popular graph database system is Neo4j. It's in position 18, which is reasonable. There's 371 systems in the ranking. So it's a bit below the likes of Cassandra and MongoDB and Elasticsearch that we've already seen, right? But it's still, I think, useful to know about this model, this database model. And there are other graph database systems. So as mentioned, this is just filtering for those systems that support graphs. We have Neo4j. We have Cosmos DB, which is actually kind of a more all-in-one multi-model kind of database. We have ArangoDB, OrientDB. These are, graph databases effectively. Virtuoso, which is RDF Sparkle. It's the directed edge label graph model. It supports also SQL queries, but it's essentially a graph database. Janus Graph, GraphDB, Amazon Neptune, TigerGraph, Stardog. So there's a mix in these between systems that support the directed edge label graphs, in particular RDF graphs, and systems that support property graphs, and systems that also support both. Okay, but these are the top 25 graph databases. So Neo4j is by far the most popular graph database available. So we're going to talk a bit about Neo4j. Let me check the time first. Okay, we have some time to continue. Any questions or doubts? Okay, so Neo4j. So what do we have? We have a graph database that was implemented in Java. Its data model is property graphs. Its query language is called Cypher. It also supports a scripting language that we're not going to talk about in too much detail. I'll give just one example at the end called Gremlin that looks more imperative in style. It's a semi-commercial system in the sense that there is an open source version for a single machine, and then there's a commercial version which gives you some additional features and support and things like that, supported by the company Neo. So there's a company Neo that's their main product is Neo4j. So we're going to focus more on Cypher to see how we can query these graphs. So the first element of Cypher that we can talk about is the match return. This is the sort of basic type of query that we can have in Cypher. And I'll provide a link to the documentation for more details. So I'll spend a bit more detail on the part that's unique to graphs, and I'll kind of lightly skip over other parts that will look familiar from SQL, or I think you won't have trouble with. So we'll spend some more time on the match because the match is something that's quite particular to graphs. So if we look at this this property graph here that we've seen before, we have a query which says match X post, okay, and it says return X. So what this is matching here is it's matching nodes labeled post. And we're going to kind of store or assign all of those nodes to the variable X, okay? So what's important to note is that this is not an ID. This is interpreted here as a variable, okay? So we're going to match an ID for post, okay? And then we'll return the nodes. So what will this return? This is the only node that matches, and it returns all of the data of that node. So it will return the label of the node. It will return also all of the properties and values associated with that node. So this is the data that we have returned. If we're interested in just returning some particular aspect of a matching node, here we're looking for matches for nodes labeled person and looking for their first name. So in this case, we'll just get the first name, not the other details of the nodes. So we can specify more precisely what kinds of data we want returned. We can also, in our match, specify some equality conditions, some conditions on the properties and values of the nodes. For example, to say, well, we're looking for a person, gender male, last name Cook. So we would have Cook and male, and we would have Cook and male here. So this will match N2 and N5. We're going to return their first name, which would be Frank and John. So we would expect John and Frank as our results. So what I'm showing here on the left is the Cypher query language, which is implemented by Neo4j. And in the Neo4j database, you would have indexed some data that would have this structure. We'll talk a little bit later about how to insert data and create data as well. But essentially in Neo4j, we can index something that looks like this. And then we're using Cypher to query this property graph effectively. So you might be asking, what if we match something and then return something it doesn't have? Okay, so we can say, okay, let's match persons, nodes with label person. Let's return their first name and their gender. Okay, so we see that matching the match clause, we have N1, N2, and N5. They have labeled person. And then we say return first name and return gender. Okay, so first name, gender is no problem, but in the case of N1, there's no gender specified. So what happens? So what happens is we'll return the results and we'll just leave a blank for gender. Because it does match X, N1 does match X, we're not going to drop the results just because the gender is not available, right? It still matches the clause of the query. So, yeah. Any questions or doubts? Okay. So, the returning value is a table, yeah, but it can be a little bit, how would I say, it can be a little bit, it can contain complex elements inside. So it can contain, for example, it can contain paths. You can return paths and you can return elements of graphs. So you can, we'll see those later. So it's not that, you know, everything in the table will have a simple value. You can also return elements of graphs as well. And also graph databases sometimes will allow you to return subgraphs. So in the case of Sparkle, you can decide if you want to return results that are tables, or you can return your results as a subgraph as well. Yeah, so in this case, generally it's useful to think about them as tables, because essentially your table here will have the columns of whatever is returned. So these will form the columns of your table, and then each solution will form a row of the table. But you can have elements of the table that are also elements of graphs. They can be paths, and in other query languages, you can also return subgraphs as well. Okay, so what about in this case, we're returning, we're matching X, and we're returning first name and gender. It's a similar example. In this case, we also match post and we also match tag, because we've not said what the label of the node should be. So we match all 5 nodes that we have here, and then we return the first name and the gender. So we'll have 5 results, 2 of which will be blank because they don't have any first name or gender. 1 of which will be blank for gender because it's not specified, and then the 2 other nodes will have the first name and the gender. Okay, so we can match edges as well. So we can match things that are connected to other things. And we use this sort of ASCII art style representation of edges. We're looking for here, X with label person, such that it has an incoming edge of whatever label from person. Okay, so, and we want to return that person. So it's like persons who have links from persons, right? So if we consider N1, it matches person, okay? And we say it must have an incoming link from a person, right? So it could be Julie. What about John? Also has an incoming link from a person, so it could be John. What about Frank? Frank also has an incoming link from a person, so it could also be Frank, right? So we get these results here. Okay, so we can end on this last example and then take a break. So what I'll do is I'll go back once. So we can stop here for the moment. Any questions?
Prof?
Yeah.
In the last example, why Julie doesn't appear twice?
So Julie has only 1 link from a person, which would be from John. Frank only has 1 link.
I got it.
Yeah.
Okay.
So you're probably counting for this one here as well. And we'll see cases like that but and this is not one of those cases, yeah, because she only has one link from a person.
Cool, thanks.
All right. So let's take a break until 15:10. I'm sorry, 15:20, and see you in 10 minutes. Okay, so we saw this example. So we'll look at a similar example. This time X is here, so we're moving it to return the person that links to another person with some edge. So which results would we expect here? Any ideas? So we're returning the first names of people that link to other people with some edge. John and Julie, right? Yeah. So Frank, no. So Frank doesn't link to another person. Linked to by a person, but doesn't link to a person. So what we have is Julie and John. Now, if we look at John, John offers 2 links to people. So what we see in the results in this case will be Julie, John. Why is that actually? No, that's not right. John should be twice. So unless I'm missing something, am I? So X matches N2, links to a person, links twice with 2 nodes, or 2, it doesn't matter what the edge is. So John should be here twice, sorry. Okay, so we'll see another example. So the multiplicity of results corresponds to the number of matches. So in this case, we're looking for persons that link to something, can be of any type. So how many times would we expect Julie to be returned? So we have 1, and this time we have 2, because we're not requiring that the thing that's linked is a person anymore. For John, we would expect 1, 2, 3. John to appear 3 times. For Frank, 1. Okay, so we have Julie twice, John 3 times, and Frank once, as mentioned before. So the multiplicity of results corresponds to the number of matches that we find, as we see. If we want to return distinct results, we will use return distinct and what we want to return. So this would get rid of the duplicates and give us Julie, John, and Frank. Okay. So in this case, we're looking for the first names. So how can we count the number of matches? So in general, it would be what we would have to consider are essentially all of the nodes that are matched by the parts of the query. So it's essentially all of the things that somehow are matched. So if we look at this node here, in the case of just say, let's say Julie, let's return here. So let's imagine that we match X to N1, okay? So then here we can match this two different ways. So we can match this will match to a node. We just haven't given it a variable or a name because we're not going to return it, but it will match a node. It can match N2 and it can match N4. So for Julie, we see that there would be 2 different matches here for this node, even though we're not interested in it. So it matches 2 different nodes, and therefore we have Julie twice. Okay. So in more complex queries, it would be equivalent to adding a variable for every node and then counting how many matches there are for X, right? So it would be like if we added a variable here, Y, we would see that there would be 2 distinct matches for Y, and that would generate two results for Julie. If we had a more complex query, we could add all the variables and then count all of the results such that X is equal to N1 to decide how many times to return Julie. If that makes sense. Actually, yes, that example works perfectly, but we'll have to return to counts. So there's an issue with group by, like, what are you grouping here? But in fact, that's pretty much the idea. So we'll have to come back to that, but that would be the general idea. And if you had more variables like X, Y, and Z, you would have to count the tuples of X, Y, sorry, let's say you'd have to count the tuples of Y and Z. So all the combinations of Y and Z that could be possible. Yeah, so it would be, yeah, okay. So we preserve the multiplicity of the number of matches. So if we don't want duplicates, we're not interested in multiplicities, we can use return distinct to remove the duplicates, as in the results here. So in this case, we're matching people who link to people, and we're interested in the first name of the first person and the first name of the second person. So we would have Julie, John, John, Julie, and we would have John, Frank. So here we get the results that we would expect, each only once because each pair only has one edge associated. So if we want, we can also define variables on edges or define some information about the edges that we want to match. So we already saw how to specify a label. Did we? No, we haven't actually. So here in this case, what we're doing is specifying a variable on the edge. So we can then return, for example, what type of relation it is. So in this case, what we're looking for are people that match or that link to other people, and we're looking for the relation, which is the label of the edge associated, that's linking the two people. So what we would get here is brother, right? So sorry, not the label, the relation. This isn't label, it's relation. So this will get us for the edge the value of the rel property, which in this case would be brother. So we still return the other elements because we're here in the return, we're not restricting the matches, right? We still match everything specified here, which is N1 links to N2, N2 links to N1, and N2 links to N5. And then we return the relation where it's available. In this case, it would be the brother. So in this way, we can also query for edges, for information about edges. So we can get some metadata about the edges in our results as well. So what happens if we just return OR? Well, it's kind of similar to what happens if we just return like X1 or X2 here. We get a description of the edge. So we get the label of the edge, and we get the properties and values that are associated with the edge. So this way we can search for on or for the data here associated with edges in a very similar way to what we did for nodes. Okay. So in this case, we're looking for Y, and we're looking for Y such that Y knows some node and Y knows some node, okay? And we are matching the first name of Y. So, okay, let's have a look at some of the examples. Y could match to N2 because N2 knows N1 and N2 knows N5. Okay, so this would seem to be a match, so we would expect the first name of N2, John, to be returned. What about N1? Well, N1 knows N2, but N1 does not know any other person, right? But could we match this to N2 and this to N2 and Y to N1? In other words, could we match these things to the same nodes? Is there some restriction on matching multiple things to the same node or the same edge? Well, in this case, match will not match the same edge twice. It can't use the same edge twice. So for Julie to be a result, we would have to use this edge twice, right? So we would have to use it here to match to N2 and here again to match to N2. So match will not reuse the same edge twice in a single result, in a single solution. So it means that we can't return Julie as a result here. We can only return John. Why did we return John twice? So we return John twice because we have one match here where this goes to N1, and we have one match where this goes to N5, and we have another match where this goes to N5, and we have another match where this goes to N1. So it's N1, N5, N5, N1, so we can swap the order of the two. Could you please repeat the process of reading that match, please? Yeah. So we can focus on Y and think about it matching Julie. Okay. And now we want, what this says is essentially it's saying from Y we have an edge nose to some node, and in this direction it says we have an edge nose to some node. Okay. So if we match Julie to Y, we can match this knows something because Julie knows N2, knows John. Now the question is, what about this one? So if we have Y knows something, it says exactly the same thing, right? So we could think N1 knows N2, which would match this again, but we have N2 and N2 used here, and we match the same edge here and here, which is the edge E1, okay? And in Cypher, match will not allow you to use E1 twice in the same result. So we can't, if we match this to E1, we can't match this to E1, right? Or if we match this to E1, we can't match this to E1. So it means that we can't return Julie as a result because there's only one edge to a person, or one edge of nodes to some node, and that's E1, and we can't use it twice in the same result. So match will not match the same edge twice. Okay. So we get John twice because we have the, we have the E2 edge and the E6 edge, and we also have the E6 edge and the E2 edge. Okay, so this is why John is there twice. Okay. Match will, however, allow us to match the same node twice if we can find a different edge. So how does this work? Well, we have a node here that knows Y, and then Y knows some other node. Okay, and then we want to return the first thing. So let's say we try to match Y to John. Okay, so what we need is that some node knows John. Okay, so this can be matched to N5, Y is matched to John, N2, and then John has to know some node, which could be Julie, right? So N1. We don't reuse any nodes, any edges, so we have, I've gotten that wrong, I think, have I? I got the edge here wrong. This N5 can't match here, so let's try that again, the other way. N1 here matches the first node here that we've drawn. Then N1 knows N2, which is Y, so Y will match to N2, which is John, and John knows Frank. So this third element here will match Frank. So Y here can very easily be John, and we don't repeat any nodes or edges. It's Julie, John, Frank, Julie, John, Frank. Okay. So what about Julie? If we try to match Y to Julie, then we say that somebody has to know Julie, which would be John. So we have John knows Julie. And what could this other node match to? So if we have Julie here, well then Julie knows John, right? It's the only option. So what we'd have is John knows Julie knows John. John knows Julie knows John. We're repeating the same node twice, but we're not reusing the same edge. We're using a different edge, right? It's E2 and then E1. So we have John, Julie, John, but we're not reusing the same edge. And this is allowed, okay? So this means that in this case, John will be a result for Y and Julie will be a result for Y. As to why we have John twice, so we spoke about Julie, John, Frank as being one match. There's also Julie, John, Julie, okay? So we can have John twice for that reason. Is that clear? Make sense? So we can match the same node twice, but we can't match the same edge twice for a single solution. Okay. So One more example of this. What we have is person. In this case, okay, what we have is a cycle. So we have person matches, it links to something, links back to X, where X is the original person node. And we're looking for that first name. Okay, so we could try to find some examples. Could it be Julie? Julie links to post, links to tag, links to Julie. Okay, we got pretty lucky. So this would seem to be a result, right? So we have Julie links to N1, links to N4, the post, links to N3, the tag, links back to N1, Julie. Okay, so that seems to be a result. What about John? John links to post, links to tag, but that doesn't link back to John. John links to Frank, links to U2, the post, but the post doesn't link back to John. It seems like we're not going to find a result for John. What about for Frank? Frank links to post, post links to tag, tag doesn't link to Frank, so it would seem that the only result here would be Julie. So there's only one match, which would be Julie, or N1, N4, N3, N1 for this here. Okay, so we can start to see that it's actually not so trivial, you know, in the general form of match to find matches. This is similar to the graph homomorphism, or arguably graph isomorphism problem, which is a difficult problem. Graph isomorphism is just saying if something like this had a match would be NP complete. Graph isomorphism is has its own complexity class, but the point being that this is actually kind of hard, this problem, as we might start to see when we introduce cycles. So in this case, just to show that we can also use as to rename, much like in SQL to rename columns and results. So we can rename x1 first name as n1. So we're looking for essentially nodes that like the same thing. So who likes the same thing here? We can quickly see maybe that John and Frank like the same thing, and Julie. So we'd have Julie, John, John, Julie, Julie, Frank, Frank, Julie, John, Frank, Frank, John, right? So because all three of them like the same thing, we create all of the pairs possible. So Julie, John, John, Julie, John, Frank, Frank, John, Frank, Julie, Julie, Frank. And N1 and N2 here become the names in the results. So they all like the same post. Why don't we have Julie, Julie? Because we'd have to reuse the same edge twice. Okay, so which we can't use E5 and E5 again. Okay. Is this okay? Any questions? Okay, so if we did want to use the same edge twice, what we can do is reuse multiple matches, and what we do between the two matches is equivalent to a natural join. So we make sure that when we do it, we join it such that, in this case, y is equal to y here, okay? So the first thing we'll find are nodes that like other nodes, which would be N1, N4 is one result, N2, N4 is another result, and N5, N4, N5, N4, three results. Next, we have in the other direction, it's essentially the same query, we just drawn it the other way. Things that like other things. So we would have N4 for Y, N1 for X2, N4 for Y, N2 for X2, N4 for Y, N5 for X2. And then when we join on this, on Y is always N4, right? So what would we expect as a result? We would expect the same results generating all the pairs possible, but now we would expect 9 results because we would also expect the Julie, Julie result. We would expect the John, John result and the Frank, Frank result. So between these two matches, we'll use a join. And this is a way to match the same edge multiple times. So in this case, we can use E5 in one match and then join it with E5 in the other match here. Okay, any questions or doubts? Okay, so this is how Cypher defines it. I'm not a huge fan. I would let everything match multiple times the same thing, and I would rather, define restrictions to say where this edge is not equal to that edge. I wouldn't have defined it this way, but this is how Cypher has decided to define it, presumably because they think it's more intuitive or more practical in this way, not to match the same edge twice. Also, I guess it helps for their paths. So this is also kind of the same idea for how they avoid cycles at paths by not using the same edge twice. So that's understandable. Okay, so Cypher, the next important aspect we have in Cypher and in general for graph databases is the ability to match paths. So compared to other graph databases, Cypher is a little bit limited in what it can match. So in other graph databases, you can match regular expressions, which are like A or B star or A followed by B star. You can create very complex expressions. This is possible in Sparkle, for example. In Cypher, what you're allowed to do is to put a star on a simple label. So you can say nose star, right? But you could say nose or likes star, or nose followed by likes star. These sorts of queries you're not allowed to do, but a simple label star you can do. So this will search for paths of length 1 or more, which is also maybe a little bit confusing because in other languages it's 0 or more. So what we're looking for is nodes x1 connected to other nodes x2 by a path of 1 or more nodes. Okay. And we're returning the first name of the first node and the first name of the second node. So we would have, okay, Julie knows John, so Julie John would be one result. Julie knows John knows Frank, so we would have Julie Frank as another result. Okay. For John knows Julie, so John Julie would be a result. John knows Julie knows John without using the same edge again. Okay, so John would be a result. John knows Frank. Okay, that's another result. And John knows Julie knows John knows Frank. We would expect John Frank twice. So here we see the results. So Julie John, Julie Frank, Julie, which I didn't mention, right? So we can go Julie John, John Julie. We have John Julie, direct link here. We have John, we have John Frank, and we have John Julie, John Frank. So we have John Frank twice. Okay. I hope that makes sense. Any doubts or questions about that? Okay. So paths visit each edge at most once. So this means that we don't get into this, we're not going to return John infinite times because we have John, Julie, John, and John, Julie, John, Julie, John, John, Julie, John, Julie, John, Julie, John, and so forth, right? So we don't consider those cases. So it means we don't have to return something like John or John Frank an infinite number of times by traversing this infinite times, which is good. Otherwise, yeah, we could have infinite paths if we didn't have this restriction. As mentioned, we could just keep looping around here as many times as we wanted. So we can also set a minimum path length. So we can set, for example, this is the number of nodes visited. So we want at least a length of 3. Right? So this would be, in this case, we're looking for nodes with a length of 3, which will give us John Frank. So this would be because we go John, Julie, John, Frank being the third node. Okay. So this specifies somehow a minimum length on our path, and it's the only pair that has such a long path. We can also specify a range of path length. So effectively here, what we're doing is we're removing the direct paths, the direct edges. So it has to be an indirect. So Julie, Frank counts, Julie counts, John counts, Julie, Frank counts, sorry. So John, Frank counts because we can go indirectly, John, Julie, John, Frank. So we get these results here. So we just essentially filter out the direct connections of nodes for the paths. So this allows us to set a range of paths, of lengths of paths. We can also specify a maximal path length using this syntax here, which will give us all the direct edges and all of the paths of length 2, which would be Julie, John, Julie, John, Julie, John, Frank. Okay, but we don't have John Frank twice, for example, because the other path is too long. John, Julie, John Frank is too long. Okay. If we wish, we can also refer to a zero length path, which will be the node itself. So this will essentially match any node. So if we do x1 and we say a 0 or 1 path of nodes, so if you've done automata, this is like an epsilon type of transition, the 0 path. So x1 links to x2. The 0 length path is essentially just a reference to the node itself. So what would happen in this case? We would get some blanks for these nodes here that have no first name. Okay, so these are matched, N3 matches here, and N3 matches here, N4 matches here, and N4 matches here. We also get Julie, John, Frank, and we get the results of the direct connections as well. So Julie, John, Julie, John, Frank. So essentially we get the first names of all of the nodes union the pairs of nodes connected directly by nodes. We can also return paths. So thus far we've been kind of returning values on the nodes. This is kind of unique to Cypher. It's not in some of the other languages like Sparkle. We can't return paths. What do I mean by return paths? I mean actually return the sequence that we followed, the sequence of nodes and edges that we followed to generate the path. So this one is x1 knows 3, x2. Okay, so minimum length of 3. So it's the path here describes first name John. It describes this node. It describes this edge, this node, this edge, this node again, this edge, and this node again. So this is an abbreviated version of it, but it gives us all of the data on that path, right? And so this is what I mean by it's a table, but the table can have some funky elements. In this case, it can have elements of the graph, which is in this case the path. So this is really messy to describe. So this is what it looks like. Okay, expanded with a soft line here, but we'll write it like this, which will be N2. E2, N1, E1, N2, E6, N5. Okay, so just what it really returns in practice is all of the data for those nodes and edges. We'll just simplify it a little bit here by giving the string of node and edge IDs used. So if we use match in this case here, we also have the option of returning just the shortest path, right? So we can match two nodes, which would be using the variables f and j, one for Frank and the other for Julie. And then we can return the shortest path between Frank and Julie in any direction. So this is any edge label, one or more of any edge label, and it's in any direction. We see we don't have the fletch of the arrow to indicate in what direction. So it's the shortest path between Julie and Frank, not considering edge direction. So in this case, we have the option of John Frank, Julie John Frank. We have the option of Julie post Frank. I guess they're the two options, right? So it will return any of those. It will return the first one essentially it finds, which in this case will be N1, E1, N2, E6, N5. There's also N1, E2, N2, E6, N5. So there's various options. So it'll return the first one it finds using an algorithm like Dijkstra, I guess. If we want to return all of the options for the shortest paths, then we can use all shortest paths, and we would get the full list of the three paths. N1, E1, N2, E6, N5, N1, E2, N2, E6, N5, N1, E5, N4, E8, N5, right? They all have the same length. So we can also query for paths, and we can even query for shortest paths, for example. We can, in this case, we're looking for the shortest path between, the shortest directed path, sorry, between Frank and Julie. So starting from Frank, we have to follow links in the forward direction. So Frank, we have to go this way, and then this way, and then this way. So that will be our path, right? N5, E8, N4, E4, N3, E3, N1. Okay, so this is a shortest directed path. So what happens if we have not just like a single source shortest path? What happens if we have multiple matches for this node here and possibly multiple matches for this node here? What it will do is it will return a shortest path for each matching pair of nodes. So for every possible pair of C1 and C2, it will return a shortest path for them. Okay. So we see here that we have 2 options for Cook and 1 option for Freud. So for each of the Cooks, we'll return a shortest path. From John and Frank, we'll return a shortest path to Julie. Any shortest path to Julie. Okay. So let me see what time it is. Any doubts or questions? Following along okay, or is it tricky? Can you store indexes? Yeah, you can index data. So you can index data. It has some specific restrictions, which can be kind of limiting, but you can, for example, index the content of specific properties to index, for example, the languages of posts to be able to find posts by a particular language. You can define particular types of indexes. All of this seems very costly. The shortest path stuff can be quite costly, especially if you're doing it on disk. If you could at least store the structure of the graph in memory, just like N2, E6, N5 without storing all of the data, then you could do shortest paths relatively quickly, but it would be in the order of the graph in the worst case. Aside from that, this is about as costly as SQL. There's no great difference between what we're doing here, aside from the path stuff, and your basic SQL queries. They have the same complexity. This might even be slightly easier because of some of the restrictions on matching the same edge multiple times. But it's in the same order of SQL in terms of computational complexity. Yeah, but of course the path stuff adds some practical expense as well, because we might have to navigate the entire, if we have a very large graph, we might have to navigate the entire graph to find matches for paths. But if that's what you want to do, there's no other way around it, and at least here you have a nice syntax for expressing such queries. Okay, so performance is definitely a concern. Yeah. So where the where clause allows us to do, like in SQL, selection criteria. So it allows us to take some results and then select some of those results, the ones we're interested in. So we can apply Boolean combinations of selection criteria. We can apply inequalities or equalities. We can apply an exists attribute to see if there exists some value for an attribute. We can use various Boolean conditions on strings, for example, that the string starts with, or it ends with, or it contains some substring, or it matches this weird syntax, which I haven't seen before in other, I don't know if there's another programming language with this, but this is that it matches a particular regular expression. So just to give, these are all things you've seen before in several query languages, also in programming languages. Just to give one example, here we're looking for the names of nodes, first names of nodes that like posts, such that the like was, the date of the like was greater than 2010, so it was somehow in the years 2010 to 2014. So if we look here, we see that Julie likes something, but it's in 2015, doesn't count. John likes something in 2014, it looks okay. Frank likes something, a post, in fact, in 2016, so that's no good. So it would only be John here, matches this condition on the edge. So here we're looking for nodes X where there exists gender. So we're looking for nodes that have a gender defined on their first names. So that would be John and Frank in this case. Starts with the J. Okay, that would be Julie and John. So we get John and Julie. And matches a regular expression, which is that we have one or more characters followed by 0 or 9 character. So in this case, we're looking for things whose name end in a number. So that would be, in this case, U2, I guess. See what I mean. Okay, so this is a standard string-based regular expression. Other features in Cypher that you've seen before in SQL, we have order by, skip, and limit. In this case, for example, we can add to the end of a query, order by the content, order by thereafter by date, descending, skip the first result and return the next one. So return the second result, ordered by content and then date descending. So this will compute the results, order them accordingly, and then return the second one, which is this result here. So this is pretty standard in terms of what you would have seen in SQL and so forth in other languages. Optional match. This is essentially equivalent to a left outer join in SQL. It's pretty much the exact same thing. So it allows us to match something and then optionally to match something else if we can find something that matches for it. So this is saying, find me nodes that where X1 knows X2. And optionally, if X1 has a follower, then give me their name as well. So this would be, for example, Julie knows John. So Julie would be X1. And Julie happens to have a follower, so we'll return that as well. In this case, John knows Frank, but John has no follower. However, we'll still return John and leave the follower name empty, right? So the follower here is U2, has follower Julie. So optionally, if possible, we'll extend this information. We have John twice here because he knows two different people. Okay, and we keep the result even though we don't find a match for has follower on John. So it's very similar to a left outer join in SQL. We have union, which again is very similar to everything you've seen before. You have union to join, to combine the results of two different matches. In this case, we're going to get an error because the column names have to be the same in the union, same as in SQL. And even if you have first name, but it's x2.first name, that matters. So the solution is to use as, right? So you could rename the variable here, right? So you could either use as to explicitly rename or rename your variable such that the names are the same. Union applies set union, which gets rid of duplicates. So if you wanted to do bag union, these are just looking for first names of people. If you want to apply bag union, you can use union all, which will preserve the duplicates in the results. So we get Julie and Julie twice because we're counting the incoming and outgoing nose links, and there's 2 of them. John 3 times, there's 1, 2, 3, and Frank 1 because he is just 1 incoming nose link. So very similar to SQL, aggregation, very similar to SQL as well. We have another query languages. We have count, max, min, average. Something that's a little bit different is we have the percentiles. We can compute the percentiles of some value in a list. So we can have an interpolation of the percentile, or we can apply it in a discrete way in terms of rounds. We also have a standard deviation, which allows us to compute some statistics over a given population. We can compute the standard deviation or a standard deviation for a sample or a population, full population. So, okay, the main things really that, people will use will still be the standard count, average, max, min, and so forth. I guess maybe some customer of Neo's really wanted standard deviations in the query language or paying a lot of money, so they added it. But the counts, what's interesting here is that you can count without adding a group by, and I quite like this feature. I think it's quite clever syntax. So what's the group by? We're doing an aggregation where we're counting x2, but we haven't said what we're grouping by. And what it does by default is that it will consider an implicit group by on whatever is not projected in the return. So if we have this aggregation function here, and we're also returning x1 first name, then it figures, okay, we're grouping by x1 first name, okay, because that isn't in an aggregation function. And this is quite nice. I think I quite like this. We're out of time. So I think there's a few more minutes left. There's not much left. There's a few slides left. Yeah. Well, not much. No. Yeah. So we'll continue this on Wednesday. I think better to stop for sure. Any questions or doubts? If not, we'll finish the class on Wednesday. I think there's just a little bit left. I hope I wasn't going too fast in the second part, but I think it's something you've seen in every query language, like limit, offset, and so forth. So I'm sure union all, and so forth. It's all SQL basically. So if there's no questions or doubts, see you on Wednesday. So this is also to mention the last class. There is one small doubt I have, which is whether we should teach the conclusions. There's one more conclusions class, which is kind of useful for talking about how different technologies are used in practice. We could do it next week, or we could do it on week 14. The idea would be after this to dedicate the time of the class to the projects. Of course, I hope you're advancing with the projects in any case, but we'll use it for Q&A sessions regarding the projects. So I don't know, any preferences? Should we teach the conclusions next week, or do you want to leave it until the last week of classes? Maybe next week, I guess, we can kind of do all the classes and then focus on the projects. Might be easier. I'm not sure which is better. I'll think about it. Yeah, so we can do it. We can do it next week, I think. Okay, so see you on Wednesday. We'll have a lab on Neo4j. Okay.
Bye.
Chao, profe,
Bye-bye.
nos vemos.
Ciao,
Chao,
ciao.
profe.